Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at Chapter 2, Matter and Changes, the first section. Now, the very first section deals with properties of matter, and one of the first types of matter that they introduce in the chapter is the pure substance, and that is matter that has a uniform and definite composition. Now remember, definite means it's the same throughout. Uniform means it is uniform throughout. You can actually have a mixture which is not a pure substance and have it be uniform if it's evenly mixed, but it's not going to have a definite composition throughout. So pure substance is also referred to as a substance. So they're synonyms for each other. So while in everyday life when somebody says substance, they usually mean matter, that thing over there, in chemistry and in chemistry class, when I say substance, what I really mean is a pure substance, which is an element or a compound. Those are things that have a uniform and definite composition. Now, one of the things we often use to describe pure substances is a physical property of the pure substance, which is a quality of a substance that can be observed without changing the substance's composition. So the key to this is there's no change in composition or product or properties. So when I weigh a chunk of ice, it's still H2O, and I haven't changed the mass of it by weighing it. So a physical property is something you can measure without changing the substance's composition. Examples of that would be hardness or color or conductivity and malleability. Now hardness, you've probably heard before along with color. Conductivity, there's really two types. It could be how well it transmits heat or transmission of electricity. Usually when we say conductivity, we're typically talking about electrical conductivity, but we can also be talking about how easily it conducts heat. Malleability is really the opposite of brittleness. So if something is not brittle, when you hit it with a hammer, it doesn't shatter, it just flattens out. That's what malleability would be. All those would be examples of physical properties of a substance. Now, there's two different fundamental types of physical properties. The extensive property, which is dependent upon the amount of substance present, and that would be like mass, volume, and length. Those would be extensive properties. When you have more, its mass is going to change. When you have more, its volume is going to change. And when you have more, its length might change. So those are extensive physical properties. An intensive physical property is one that's independent of the amount of a substance. Things like density, absorbency, those would be intensive physical properties. Density is a big one. Density is something that you've probably seen in math and science class. It's the mass divided by the volume. So it's really a ratio of two extensive properties, but as a ratio for a pure substance, the mass to volume ratio doesn't change. So it would be an intensive property. So whether you have a little bit of water or a lot of water, its density will be the exact same. So while the mass and volume change, the ratio of the two would not. So that's a really common intensive property in science. Now the next thing they get into in this introductory chapter is we talk about the states of matter, which you should have a pretty good working knowledge of at this point. Now, first we're going to look at the solid. And you need to understand what's happening at a particle level and what's happening between the particles here. So I want you to have a good visual understanding of what's happening inside a solid. Now, as you probably already know, solids are packed close together, and that's because they have strong forces holding them together. And it really keeps the solid locked in place. Now, this is a common image off here on the right in the middle of what a solid might look like. And you'd notice the particles are packed close together. The problem is it's a picture, and the animation above it, so this is what I want you to concentrate on here, is probably a little bit better visualization of what a solid really looks like. You'll notice the particles are packed fairly close together, but there is some space in between them. And the particles are in constant motion, but they're not getting anywhere. And that's really a better visualization of what a solid would look like on the particle level. And the reason why those particles are close together is because there's strong attractive forces holding them in place. They're free to move, I should say they're free to move and vibrate, but they don't move to a new location. So particles vibrate, and that's really because they're held together too strongly to break away. If you move fast enough, you can break away from attractive forces holding you back, but the solid particles aren't moving fast enough to break that strong intermolecular attraction that holds those particles together. Now, because they're packed close together, and it's very hard to push them any close together, solids have a constant volume and a constant shape. So you can see in the bottom of the container here in the picture on the right, which shows relative temperature in the particles, you can see that they're clumped together. So they have their own shape and they have a constant volume. And there's very little space in between solid particles, which makes it very, very hard to push solid particles any closer together. So we consider them incompressible. And that's also a property we'll look at with liquids in a second as well. So that takes us to the liquid. You'll notice in the picture our temperature of our substance is a little bit higher. And one of the things I want you to have a working understanding of throughout the year in chemistry is when you have a substance and you dump energy into it, you heat it up, what happens is on a particle level, the particles start to move faster. So in the case of a solid, they vibrate faster and faster and faster. Well, think of it like an earthquake. If you vibrate a building fast enough, the building starts to break apart. And that's what happens when we become a liquid. You'll notice in our picture over here on the right that our liquid particles are a little bit farther apart than they were before. And that's true of most instances. But the movie that I'll want you to watch associated with this, which you can link to on the Haiku website, you'll notice in the movie that it actually talks about ice, and ice versus liquid water is one of the rare things that would not be true. Normally, liquids are a little bit farther apart, but because of the shape and bonding in H2O, as a liquid, they actually end up slightly closer together, so it expands when it freezes, and that's very rare with substances. For most things, as a liquid, it's going to be expanding just a little bit, unlike what happens with ice to liquid water. Now, in liquids, particles are farther apart, and that's because they're moving fast enough to partially break away from those around them. One of the things we're going to use and talk about periodically is, what affects attractive forces? Well, distance can lessen attractive forces. Think of holding a refrigerator magnet a little bit farther away from the refrigerator. And speed can also overcome attractive forces. Think of lightly throwing the refrigerator magnet against the fridge versus throwing it very hard. So as you start to move faster, the kinetic energy of the particles start to overcome those attractive forces. Those are two opposing forces, and which one wins depends on whether you've got a solid, a liquid, or a gas. So in a liquid, they've partially broken apart and the particles are moving faster. But the particles still stay together. They do have attractive forces because they're not moving fast enough to totally escape and become a gas. So we still have a constant volume, but now we take the shape of the container. So you'll notice instead of a clump at the bottom of our flask here, our particles have basically flattened out and they're taking the shape of the bottom of the container. But liquids still do have a constant volume, and like solids, they're considered incompressible. It's very hard just to physically push the particles any closer together, because typically they flow, so they just deform and move. So liquids and solids are incompressible substances. Now, if we keep heating up a liquid, the particles start moving faster and faster and faster, and eventually you're moving fast enough that with just a little bit more energy, you could totally break the force of attraction holding you together, and you can go anywhere around you. And that would be our gaseous state. So one of the things that separates the gas from our liquids and solids is now our particles are farther apart and they have no attractive forces. The speeds of the particles have overcome the attractive forces and made them irrelevant. So your particles in general compared to solids and liquids are moving very fast. And in this particular state, we have no constant shape or volume. So we can actually compress our gas. So gaseous state is the one state that's clearly very different from the solids and liquids. And as you think about what is talked about here, from your middle school and elementary school discussion of states of matter, these things should become, should sound familiar to you. But understanding at a particle level, that may go at a little greater depth than what you saw before. Now, while we're talking about gases, I want to talk about a particular type of gas, and that's a vapor. Vapor is matter as a gas that's usually a liquid or solid under the temperature and pressure conditions that it's existing at. So in this room right now, if I had water, H2O, it will have melted and it will be sitting as a liquid. But some of those liquid particles evaporate and become a gas. So even though water is typically a liquid in my room, under the temperatures and pressures that exist there, it can exist in the room as a gas, and we refer to that as a vapor. So all vapors are actually gases, but not all gases are vapors. It's kind of like the square rectangle idea, and that's because other gases which are in the room with me, about 80% of what you're inhaling is nitrogen gas, about 20% is oxygen gas, and those comprise most of what you're breathing in inside the room. Well, those two gases are gases under room temperature and pressure conditions, so we don't refer to them as vapors, we refer to them as a gas. Now, the fourth state of matter I just want to point out because our understanding of solids, liquids, and gases kinds of builds to this point, and that's the plasma. Plasmas are a state that's at very high energy and temperature, and what you really have is a charged gaseous particle. Now, how plasmas actually form kind of makes sense if you walk through what's happening. You've got a solid, the particles are moving relatively slow compared to liquid and gas. Intermolecular forces are so strong, it holds it together in a clump. But as you heat it up, the particles start to move faster, and eventually they move fast enough to start to break away, and they melt and become a liquid. After they've melted and become a liquid, now when we dump in energy, once again, the particles start to move faster, and eventually they're moving fast enough to break away and become a gas, and we boil. Well, if we keep dumping energy into a gas, eventually we dump in enough energy, we start to break the gas apart. And as you may remember from your earlier science, protons and neutrons are in a very small region inside the atom called the nucleus, held together by very strong forces, and somewhere outside the nucleus we have our electrons. So when we dump in enough energy to actually start to affect an atom, what we're doing is knocking out electrons. And that's why a plasma is a charged gaseous particle. We have gas particles that are moving around. Those are our plasmas. Now, if it is a neutral atom, the protons and electrons inside are equal to each other. So if we knock out one of those electrons, what we're left with is a positively charged particle. So if I draw that better, instead of a positive and a negative inside, our electron is left, and what we're left with is a positively charged particle. So that's what a plasma is. It's a highly unstable thing because, as you know, opposites attract. So when our plasma particle gets close to an electron, it will quickly reabsorb it, and we won't have the plasma anymore. We'll just have a high-speed gas particle. Now, plasmas are relatively uncommon and unstable and don't exist for very long as far as a state. So we don't work with them in an everyday basis, but plasmas actually get created in a number of different everyday situations. Probably one of the ones that you may be most familiar with is the aurora borealis, the northern lights. That's a plasma being created in the upper atmosphere, and it shimmers. It turns on and off because as it gets formed, it starts to release light, and then when it reabsorbs the electron, it ends up going back to a gas again, and the light turns off, so to speak. To a small degree in flames, neon signs, in lightning, in a lot of different situations, plasmas do exist in the world around us. And it's kind of a natural extension of understanding what happens as we go from a solid to a liquid to a gas. Now, State of Matter movie is just a recap of some of the things we've talked about. I'd link to it online and watch it. It's short and it does a good job of reviewing some of the stuff we just looked at. Now, next is dealing with physical changes. We talked about physical properties of a substance. A physical change is when we have a change in appearance but not in composition. So we've changed at least one property. We tore it in half, so we've got a smaller mass. We have a smaller volume, and so on the particle or on the particles that are left after we tear it in half. So we did have a change of appearance, but it's still paper. So if you take an ice cube and break it in half, that would be an example of physical change as well. Another thing that would be a physical change is if we melted the ice cube. It looks different than it was before, but it's still H2O. So we still have the same chemical composition. Those would be examples of physical changes. Now, physical changes like changes in state are actually always reversible physical changes. So some physical changes are reversible, some physical changes are not. But when we're dealing with changes in state, all changes in state can be reversed. Add some energy, you melt the ice into water, take some energy out, and you reverse the process. You freeze it back into a solid. So some physical changes are reversible, and a good example of that would be changes in state. Like I said, those are always reversible reactions. And some changes in state are irreversible, like tearing a sheet of paper. I can't just sit the two pieces together and they rebond again. So some physical changes are reversible, some physical changes are irreversible. Now, that ends our notes over section 2.1.